I'm Gabriel Pasquet, and I'm a postdoctoral researcher at the University of Po in France. And I'm going to present the production of hydrogen in geothermal system, and particularly in volcanic zones, with the case of the Assal Goubet Rift in Djibouti. To start here is a map of the world heat flow with the site where natural hydrogen has been found superimposed. There are many other, we need to update this map, but we can see that in addition to continental cratons, more prone to radiolysis, for example, and serpentinization related ophiolites, there are hydrogen sites in areas of high heat flow, like on the Atlantic Ridge, on the East African Rift, or along the Pacific Ring of Fire, for example. One of the great assets of hydrogen is that it can be formed by a wide variety of natural reactions, from mafic rock such as basalt to ultramafic rock such as peridotites, with a well-known serpentinization reaction. We talk a lot about it in the previous presentation. To felsic rocks also, such as granite from biotites or amphibole. In these various cases, the process involved is the oxidation of ferrous iron contained in certain minerals to ferric iron, coupled with a reduction of water to hydrogen. These reactions are possible over a wide temperature range, but have different production peaks depending on the phase involved. An alternative to water is the production of hydrogen, particularly in volcanic or hydrothermal system, is H2S. During degassing, it can combine with the omnipresent water in volcanic system to form SO2 and hydrogen. Or it may combine with an iron phase to form pyrite or chalcopyrite and hydrogen. Thus, the presence of pyrite in the rocks of the system can be an indicator of an hydrogen production. Here is a plot showing hydrogen generation as a function of temperature. We could deduce that the higher the temperature, the more hydrogen is produced, but we note that there is a lack of data below 150 degrees. Experiments are mainly focused on peridotites and olivines, but magnetite, amphibole, and siderite, for example here, are also interesting hydrogen-generating minerals. What can also be said is that there is a lack of data for reaction involving H2S, and therefore potentially pyritization. Now, to present a case study of hydrogen exploration in high-temperature geothermal area. So I will start with the East African Rift. This large system opens up along three main axes in the north part, I would say. So the Red Sea, the Gulf of Aden, and the main Ethiopian Rift. The floor and accretion axes are essentially basalts. Field studies were carried out to assess the hydrogen potential of some existing and future geothermal prospects, like in Tumlumoye in Ethiopia, for example, or in Tendao or Dalol in Ethiopia. Various sites stand out, and I'm going to focus only on one of them at Lake Assal in Djibouti. Here. The Assal Rift consists mainly of fissural basalts with stratoid series on the margin in green and axial series in the center, here in blue. Large fault perpendicular to the opening extent across the rift allows water to circulate from the Bay of Goubet to the Lake Assal. Here in yellow dots, we have some hot springs or from some thermal springs. Geophysical studies reveal various anomalies at depth and the seismogenic zone beneath the Fiale caldera, here and here in the map. Since the 80s, many geothermal wells have been installed in the Assal Rift, and hydrogen has been measured at depth in the external margin up to 0.25% in this well here in the southwest margin. Our surface survey shows that hydrogen emanation are present in the axis next to the Fiale caldera, here site 4, for example. But we didn't measure any hydrogen in the margin at surface in the fault, for example. XRD data coupled with temperature in the wells shows that basalt are present in the axis with little or no potential cap rock, only fresh or least fresh basalt. But we note the appearance of secondary minerals such as calcite, chlorite, pyrite, and epidot here at the temperature maximum over 200 degrees. And there is also a temperature inversion in the axis after 500 meter depth explained by an intrusion of marine water in the axis. So now secondary minerals observed in XRD are not in equilibrium anymore with the current temperature in the wells. In the margins here, there is a thick cover cap rock with yellow clasite and a clay layer, but the well is not deep enough to see what is below and if there is some fresh basalt, or at least see the composition of this basalt. Furthermore, if you want to know the remnant potential of our basalt, considering a reaction where all the iron 2 is converted into iron 3, so it's very hypothetical, we can see that the chlorite here, all the brown dots here, so the chlorite from the propylitic geothermal zone are the most promising, with an ideal production of 32 liters of hydrogen per kilogram of rock, based on this number of 1,332 millimole per kilo of rock, based on dehydrogenation of chlorite. It's a theoretical number. It's only if all the iron 2 from chlorite goes into iron 3 on iron 3 chlorite by dehydrogenation. This reaction is mainly it's optimal, above 390 degrees approximately. So it's very high temperature. But here we can't talk about serpentinization because we are in basalt, so there is very few olivine, and hydrothermal reaction in basalt will mainly produce iron 2 clays like smectite or chlorite minerals, secondary minerals. So pyritization also, reaction from magnetite, for example, are not to be underestimated and are an essential potential source. So we measured hydrogen in the axis surface, but not on the margins. And we measure hydrogen in the margin at depth, but there is no data available on gas content in the axis, unfortunately. So the first deduction that can be made is that cap rock is present on the margins, here potentially clays and yellow clasite, but nothing in the axis, because we measure all the hydrogen in fumaroles, and there is on huge faults connected directly to the volcanic chamber. In this case, the origin of hydrogen is diverse, involving volcanic degassing, connection of axial faults to the magmatic chamber, volcanic chamber. Also pyritization, because we observed in XRD some pyrite in our cuttings, So maybe there was some pyritization reaction before that has already produced hydrogen. And also potentially chloride oxidation, so by the reaction of dehydrogenation. But we need to explore more this kind of reaction with kinetic data. So, but what is interesting is that this propylitic zone in green in the sketch is interesting because it will act both as a source rock for hydrogen generating work and also as a geothermal reservoir, because in geothermal system, propylitic area are the more focused one for reservoir.
You're at 10 minutes.
Perfect, thank you. And so the hydrogen will migrate by those active fault and seismogenic area that we see with geophysics data. So finally, the hydrogen is produced by many different reactions, which can be combined and is enhanced by the high temperatures of the geothermal fluids circulating in these rocks. The advantage of volcanic region, such as East African Rift, but also Iceland or New Zealand, for example, is that despite lower hydrogen concentration, as serpentinization reaction, for example, or in craton, the gas flow is significant and continuous. On the large majority of this kind of sites, there is already geothermal wells in production or in exploration. So to simplify, so all that is needed now is to recover this hydrogen by gas separation, for example. Also, what is required now is long-term monitoring on this hydrogen, particularly at depths, in order to identify the reservoir and cover to define hydrogen system. And also with a 3D model to see the extension if it's not focalized under the Fiale caldera, for example. Geothermal data are essential to understand the hydrogen system with data on temperature, fluids, gas, and geological formation at depths. Thank you for your attention.
Thanks a lot. So we have plenty of time for discussion questions. So if you have some, you can raise the hand. Otherwise, I see that in the chat there is a question from Tobias. Yeah, Tobias, you're welcome to ask your question if you want.
Okay, yeah, thanks. Thanks, very interesting talk. I have one question or two questions. First of all, so you mentioned this cooling in the lower part. This is evidence for seawater cooling. So what are the detailed evidences for this? And then the next question is, in your sketch, in one of the slides at the end, you basically indicated that there is an upflow. And I want to ask the same, what evidences do you have for the upflow?
So here on the sketch for the inversion of temperature at depths, there is hydrogeological data. I didn't make them, but there is water composition measurement, and so it's close to the water that here infiltrate through these faults. And yeah, so mainly that it's based on water composition at depth here in the geothermal wells. Is that answering your question, your first question?
So these are downhole samplings, or these are wellhead samples, or?
Yeah, so for my XRD measurement, it's based on cuttings. I worked with the geothermal company there in Djibouti, and so I have access to water analysis. And there is some published paper by Sanran, I think, also with water data.
Okay.
And
Yeah.
the second question was here.
Yeah.
What again? Sorry.
So all the results from the drilling basically indicate that the VR levels are located in an outflow zone. I'm a little bit surprised that you somehow infer an upflow or somehow fluid migration. So what evidences do you have for that?
The outflow, you mean from the volcanic chamber?
Yeah.
It's only because we measure the hydrogen in fumaroles here, and all the other fault without fumaroles or high temperature hydrothermal zone or alteration. We only measure high hydrogen content in these fumaroles, and fumaroles so are linked to the volcanic chamber.
Okay.
Okay.
That's it.
I think
Thanks.
we can move to the next questions. If you want, you can continue the discussion afterwards. But we have two other questions. Robert, you were the first one.
Yes, this is a question maybe for all the speakers. I'm aware that at moderate temperatures, hydrogen can diffuse through many kinds of things. I wonder, does anybody have an idea how to store the hydrogen gas once you've isolated it?
I can maybe comment a little bit on that.
Yeah.
So what by storing, do you mean when you get it out and you want to store it somewhere to use it, or somewhere geologically? Because indeed hydrogen can easily, it's very small, so it escapes very easily. So in a geological context, you would like to have maybe a salt layer or something and a reservoir layer below in which it can be captured. And ideally, it would still be sourced by an active source. So there would be substantiation going on, or maybe like, substantiation of your mantle, or maybe of basalts, or something like that. And then if it can be permanently sourced, then we have a good chance that that field actually remains full, I would say. Otherwise, if it's very old, then if it's a very old system, a fossil system, let's say, it's not like petroleum where it might be able to remain. So then there's a small chance that we can actually use it. I hope that helps.
Okay, thank you.
We can move to the next raised hand. Jürgen?
Yeah, thank you very much. It was a great presentation. Maybe I just can quickly add to the last question. We do have helium reservoirs, keep in mind, and the helium atom is a similar size as hydrogen molecules. And we have them stored since 100 million years, some of them. So there is a potential to store gas molecules of that size geologically over a longer time. We haven't found, of course, hydrogen ones. But let me ask my question, and that is related to the geothermal valves. Pascal, you have mentioned you have found hydrogen content in the gas of 0.25% maximum. And we see kind of small numbers like that actually also from Iceland if we look at some of these geothermal wells. If we go to other places, we actually see 90% or even more actually in aquifers. If you go to Kansas, for example, or if you go to Mali, you actually can see aquifers which actually have much higher contents of hydrogen. Can you let me know what your thoughts are and how to explain these things?
So sorry, it was for me.
Yeah, it was for you. Yeah.
Okay. Sorry. Can you repeat the question? Sorry.
Yeah, we see in you've just shown that in the Assar Lake you see quite low percentages of hydrogen in the geothermal waters. And we see a similar thing in Iceland.
Yeah.
But we see other places, like in Kansas or in Mali, where we get above 90% hydrogen. How do you explain these vast differences actually kind of, well, aquifers, maybe they are different geologically, but there is vast differences in percentages of hydrogen which you may measure from such aquifers or geothermal wells.
Yeah, so I think there is plenty of explanation. For example, so we talk a lot about the protolith and rock reaction involving the production of hydrogen. So if your rocks is already doesn't have the parameter required in iron 2, iron 3 on mineral required, you will not form as many hydrogen as you want. So there is no hydrogen available in the to go through in the water, for example. But there is also a question of salinity that me personally, I don't have the data on the kinetics and solubility in salinity, but we see that depending on the water source, depending on the salinity also, you will have less solubility for hydrogen. But I don't remember, sorry, if it's with high salinity value, you will have more hydrogen in the water. I don't remember, sorry.
Thank you.
Yeah.